Hello, this is Mr. Gilmore with the 10.5, the side angle side and side triangle area. As it turns out, the area formula we derived in our 10.3 lesson is not the only area formula that we can find with a triangle. The side angle side and the side are two other pieces or two other triangles with the given information that we can actually find the area of the given triangle with that given information. So as it turns out, we're going to derive the side angle side area formula, but we will not derive the side. I will talk about the nature of it, and if you're curious, I'll point you in the right direction of watching the derivation of the side triangle area. So where we start is actually deriving the side angle side area, and then we'll move into looking at the side case, and then we'll finish off the lesson with a couple examples. So let's say, for example, we're given a triangle with the side angle side pattern, which means let's let our side lengths of a triangle be represented by the side lengths of A and B, and then let's let theta represent the included angle between those two sides. What we're going to do is we're going to come up with a way to find the area of this triangle. Now, as of the moment, we only have one method kind of under our belt in which allows us to find the area of a triangle, and that is the area of a triangle equals 1/2 base times the height. Where B, remember, represents the base and the height is that perpendicular to it. Well, if we're given a side angle side information, that means we can choose any of the two sides to be a base. And then the perpendicular, the height to that base, would then obviously be the altitude from the opposite vertex. Well, what we're going to do here is we're going to choose our side A to be our base. And what we then will follow through with that is by dropping the respective height to that base. So it's going to be the altitude formed from the opposite vertex. So from this opposite vertex, let's go ahead and drop in our altitude till it intersects our opposite side there, our base, at a right angle. So we're call this then our h. That is going to be the length of our altitude or the height of our triangle. So with our dimension of a chosen as our base and h, we could find the area of this triangle. But remember, h is not one of the given pieces of information. What we're given are the two side measures and the included angle. So the question we ask ourselves is, can we actually then put the derivation of the formula in terms of the three pieces of given information, the two sides, A and B, and the given included angle, angle alpha? So if we take a look, a good quick look or a good deeper look at what we've just done with that altitude dropped in, we form ourselves a nice looking right triangle here. And as it turns out, we really like that right triangle, and here's why. We have the acute angle measure, the theta, and we have our side B, which is actually the hypotenuse. As it turns out, we now have a relationship between, amongst the angle that's formed there, angle alpha, the height, right, h, and our hypotenuse of that right triangle, side B, which, if you think or recall, or side B is what was given to us to begin this derivation. So what we have is, by definition then of our sine function, sine of our angle theta is equal to h over the side B. Okay, now be careful. The B here in our area formula, this is not the same as the side B, right? This is the base, right, for the area. This is the side given, okay? Now, what we can do with this definition of sine of theta is we can then solve to isolate our value of h. So h then is equal to B, because I can multiply both sides by B, times the sine of theta. Now, why that's important is because we can then take our equation that we do know to find the area, which is 1/2 base times the height, and we may replace the height with this respective equal expression, b times the sine of theta, and we know we've chosen the base of our triangle to be the side length of A. So we're going to replace then the value of the base with the respective variable A, and what we then get is a new form of the area of a triangle, and this new form of the area of the triangle is going to be in terms of the two sides and the included angle it's given. And it looks like this. We take the 1/2 still, we replace the base with what the variable was we chose as the base, which is our side A, and that's being times by our value of h, but we replace h with its respective expression, which is b times the sine of theta. And what we have then for ourselves is a nice shiny new formula to actually find the area of a triangle using the side angle side given information. And so what we unpack this to find is that this pattern is actually going to be the same no matter what side angle side information we're given. As we unpack this, we can put this then into words, which we'll see here on the next slide. But this is actually our new derivation of the side angle side area formula. So the original equation we proved, the area of the triangle 1/2 base times height, that handles those cases where we are able to find the height and the base of a respective triangle. But now if we're given any triangle with the side angle side pattern, we can also tackle that one with our new formula. So let's unpack what we just saw with the side angle side area derivation here. What we just happened was that we found the area of the triangle by this. We found it by taking half the product of the two pairs the product of the pair of given sides times the sine of their angle included. So we find that the side angle side information is enough for us to find the area of a triangle simply by taking, again, half the product of the given pair of sides times the sine of their included angle. And so you're going to find this the derivation of the side angle side formula on your postulate theorem handout. So be sure to take a look at that and realize that that's another tool we have uh, to actually find the area of a triangle with that given information. Let's now take a look at our side case. The side area formula actually introduces a quick definition, and we are going to accredit this to a famous mathematician, actually an ancient Egyptian mathematician, and I'll talk more about that here in just a second. So where we begin with is a triangle with the following side lengths of A, B, and C. Now, the letter S represents what we call the semiperimeter. We actually saw the semiperimeter vaguely, just a little bit, in our chapter 5 when we talked about the triangle inequality theorem. And what we recall the semiperimeter to be is just simply half the perimeter. So if we're given a triangle with side lengths A, B, and C, the semiperimeter would just simply be the sum of those three sides and then divided by 2. And so once we find that perimeter, we associate the variable S, or should I say the semiperimeter, we associate the variable S with that, the length or the measure of that semiperimeter. Now, what we have then at our fingertips is a beautiful equation, beautiful expression that actually will calculate the area of a side triangle. And that is what we find right here in the middle of our slide. This square root of this product of four factors, S times the difference of S and one of the sides A, times the difference of S and the another side B, times S the difference of Fs and our last side C. And what we'll find is with the product of these four factors, taking the square root of it, will actually deliver the area of our given triangle with a side pattern. Now, if you're curious, we like to call this Heron's formula. It is associated or accredited to the mathematician known as Heron of Alexandria, and he was a famous ancient Egyptian mathematician, and he spent a lot of time actually deriving this formula for us. If you're curious, Google Heron's formula, and if you'd like to see the derivation, Khan Academy actually has a very good explanation of how this is actually derived. So if you'd like to actually see that, I encourage you to go and watch that. We're not going to take the time to look through it because the derivation of it is a bit tricky. So I encourage you to find a source that will walk you through it accurately. What we're going to do to close out our lesson is by looking at an example of using both of our newly found area formulas, the one for our newly derived side angle side, and this one given to us, the side. Let's start with a side angle side example. Let's say we're given a triangle with side lengths of 12 and 18, and their included angle that measures 45 degrees. Find an exact expression for this area. So what we're going to do is, if you'd like to, you could draw a picture. So we're going to draw a quick picture of our triangle here. I've got the side length of 12 and 18, and the included angle is an area, sorry, the included angle is a measure of 45 degrees. Now let's unpack that area formula we derived for our side angle side. And the way we see this on our postulate theorem handout looks like this. It's the area of our triangle is 1/2 times the side sub 1 times the side sub 2 times the sine of their included angle. So S sub 1, S sub 2 just simply means the two sides given, and alpha is the angle that is included, the angle between the two given pairs of sides. So this does ask us to find the exact answer, and here's why. When we plug our values in, we get 1/2 times 12, that's one of our sides, times 18, doesn't matter which order we plug our side measures in, times the sine of the included angle. Notice that the included angle is one of our special angles. Think back to our trig chapter where we finished, or we look at the special right triangles, the 45, 45, and the 36, 90. But when we found the 45, 45, and 36, 90, we mashed that together with our trigonometry, sine, cosine, tangent, and we found that the sine of 45 gives us a nice, clean ratio that we actually know the exact answer of. And so let's go ahead and evaluate the finding the area of this triangle. I'm going to start by actually multiplying our rational values right here in the front. So I'm going to do 1/2 times 12 times 18, and what we evaluate after we just multiply those three values together, I get 108. And that's still multiplied by the sine of 45. But the sine of 45, remember, is going to give us a nice ratio. And the ratio we get, if you have to look back in chapter 8, we got the ratio of root 2 over 2 is our sine of 45 degrees. And so now we multiply 108 times root 2 over 2, which simply means just divide that 108 by 2, and we end up with our final answer, 54 times the square root of 2. And there is the exact area of our triangle, the side angle side. Now, in some cases, we're not going to be given our nice angle measures of 45 or 30 or 60, which then means we are going to have to use our trig table or our calculator at that point to take our included angle and then change that into its respective ratio, and which means you will have to then estimate or give an approximation of that ratio. So your answer will not be exact, but it will be a close approximation because of the nature of the angle measure given. So just be on the lookout for the worksheet with side angle side, that you may actually run into some situations where you're not going to be able to get an exact answer. All right, but we do go back to that derived area formula, so make sure you have that on hand when jumping into the homework assignment. Now let's finish off by looking at a side example where we're going to be given the three sides, and we're going to calculate again the exact area. And the reason why we can calculate exact area is because our equation, or expression to calculate the exact area using Harris formula, is it's going to give us the square root, which means we can simplify the square root values of the product of the four factors we find on the inside. So where we begin with our adventure is simply finding the semiperimeter. Again, we let S represent our semiperimeter, and S is then, remember, the sum of all three sides divided by 2. So I'm going to do 12 plus 18 plus 24, and we're going to divide that in half. 12, 18, and 24 make 54. Divide that by 2, and we get our semiperimeter to be a length of 27. Now, to do a quick check for yourself, the semiperimeter of a triangle should always be greater than any of the given sides. So just do a quick check. Is 27 greater than all three sides? Yes, it is. If it's not, that means check your semiperimeter calculation again. You want to make sure that semiperimeter is going to be greater, and it will be greater than any of the three sides. It's actually one of the triangle inequality corollaries we proved back in chapter 5. Now we've got our semiperimeter, let's dive into finding the area of this given triangle. So the area of a triangle, I'm going to write out Heron's formula for us. It's S times S minus A times S minus B times S minus C. All right, and that's going to give us our area. So A, B, and C representing just the three sides of our triangle. So we're going to plug our values in. So I have 27 times 27, I'm just going to go in order, minus 12, times 27 minus 18, times 27 minus 24. Now let's go ahead and simplify each of those into their respective factors, and then we will simplify our radical as a whole. So I saw that 27 out front. 27 minus 12 is a factor of, or a value of 15. 27 minus 18 is a value of 9. And then 27 minus 24, we get a value of 3. Now, what I'm going to be on the lookout for now are perfect square factors. What I'm going to do is actually I'm going to put together a few of them to make me some nice perfect square numbers. 3 times 27, as it turns out, if you multiply the first factor and the last factor, which we're allowed right to regroup and reassociate our factors, which means I can multiply those together, and what I get is a value of 81, which turns out, hey, that's a perfect square. 9 is also a perfect square, so I have that 81 times 9, and then 15 is not a perfect square, but I'm going to tag that on the very end because we'll find that 15 will be stuck on the inside. So now I can actually simplify that. I can take the square root of 81, which spits out a 9. The square root of 9 spits out a 3. And then the square root of 15 is, the factor of 15 stuck on the inside of our radical there. I can then finish off by multiplying our outside numbers together. 9 times 3 is, in fact, 27. And that factor of 15, again, is stuck on the inside. And that's as far as we can simplify it. So there is our area of our side-side-side case of our triangle, and we can give it exact form. But once again, in the worksheet for the 10.5, you're going to come across some triangles side-side-side where the nature of the problem starts you off with decimals. And if it starts you off with decimals, then I'll be okay with you actually give me an approximation because simplifying with decimals is possible. It's not the it's not the prettiest game to play. It is possible, but let's just say that if you do start off with a decimal given to you as your side lengths, then I would feel comfortable with you just giving me a decimal approximation in return. All right. So we've come to the end of our 10.5 lesson on looking at our two other special cases of finding the areas of triangles, the side angle side and the side-side-side case. If you have any questions on that 10.5 homework assignment, please do not hesitate to email me. With that, be good and do good.